Here's the problem that we had from before that I posted in the Google Classroom. So I want you to see it, and then I'm going to stick it at the front of the video I already recorded. We're going to consider a star with a mass 1.5 times the sun's mass and a density similar to that of the sun. The star rotates once every 30 days. It's going to become a neutron star with a radius of 15 kilometers, and we want to know what is its new rotational speed. Express the final answer in units that are meaningful to you, and you can look up any values that you want. Alrighty, very good. Okay, this is my solution of the problem that I posted in Google Classroom, which is finding the rotational speed of a neutron star. And in that problem, I said that the neutron star has 1.5 times the mass of the sun. That's the notation we use for the mass of the sun. And we said that it rotates one time every 30 days. And we wanted to know what would its rotational speed be if the radius is reduced to 15 kilometers. I told you before that this is a conservation of momentum, angular momentum problem. So angular momentum, well, remember linear momentum is mass times velocity. In the angular case, L is equal to the analog of mass, which is the moment of inertia, times the angular velocity. So the initial product of these two will be equal to the final product of the moment of inertia and the angular velocity. Now, the question is, what is moment of inertia? And the moment of inertia for a sphere is equal to some factor, I'll just call it F here. I believe it's 2/5, but you can look it up, times the mass times the radius squared. And so we could write this as L equals some factor times the mass initial times the radius initial squared times the initial angular velocity is equal to some factor times the final mass times the final radius squared times the final angular velocity. And what you can see immediately is that this factor doesn't matter, whether it's 2/5 or 1/12 or whatever it is, doesn't matter. And since the mass doesn't change, by the way, the factor doesn't change because it's still a sphere, we're not changing its shape. The mass doesn't change because all the mass is changed to a smaller volume. It's becoming much denser. So really, to find the final angular velocity, we just need to know the initial and final radius and the initial angular velocity. Now we know the final radius is 15 kilometers. That's given in the problem. And we know the initial angular velocity is equal to 1 revolution, or 2 pi radians, 2 pi in one time around, in 30 days. And we can convert that to radians per second, because we know that 1 day is 24 hours, and 1 hour is 3,600 seconds. So that'll give us in radians per second. And it's going to be a small number, right? It's about 6 divided by 30 divided by 24 divided by 3,600. Very small number of radians per second. What we don't know is the initial radius. And in this problem, I told you that the density of this star was the same as the density of the sun, and it's 1.5 times the mass. So here's how we can figure this out. And I'm going to take a little shortcut here, but not too much. Let me slide that up a little bit. So the mass of our star is 1.5, sorry, nice, 1.5 times the mass of the sun. Since mass and volume are directly related by the density, the volume of our star is 1.5, did it again, 1.5 times the volume of the sun. And since the volume of a sphere is 4/3 pi times the radius of our star cubed is equal to 1.5 times 4/3 pi times the radius of the sun cubed. 4/3 pi cancels out, and we have that the radius of our star is equal to the cube root of 1.5 times the radius of the sun. And we can look up the radius of the sun. I looked it up on Google, and it was, I don't know where it is, but actually I didn't look it up on Google, I guess. But we can find that and then just take the cube root of 1.5 times the radius of the sun. Well, this is the radius cubed, if it's going to be under the radical. Okay, so now our problem becomes, I'll just leave all the variables in here. Up here we have L. Okay, let's solve this for omega final. Omega final equals omega initial times R initial squared divided by R final squared, which will be whatever number we get out of here, times R initial. This is our R initial, the radius of the star. And R final is 15 kilometers. So we do have to have this in kilometers. Okay. So I'm going to stop recording here and I'll look up some values. And I also see it's noon, so we'll finish this after the lecture. Okay, I just watched that lecture with you guys on converting between linear and angular measurements and so forth, and had a conversation with those of you who were logged in. And then while I was gone, I looked up a couple of values. I looked up the radius of the sun, and that is 696,340 kilometers. Let me see if I can focus that any better. 696,340 kilometers, and we multiply that by the cube root of 1.5, and I get about 800,000 meters, or 7.97 times 10 to the 8th meters. And up here, I just went through and put this in my calculator to get the rotation of this star when it's a star. This is the initial angular velocity, and it's 5.82 times 10 to the negative 5th radians per second. So it's a very small number of radians per second. And remember, it was one revolution in 30 days. So 10 to the negative 5th radians per second. So putting that in for our initial angular velocity, putting this number here for the initial radius, and putting 15 kilometers, and I wrote that as 15 times 10 to the third meters, for the final radius, we can now calculate. We take 5.82 times 10 to the negative fifth times the square of this ratio, and the answer that I get is 164,307, which is way too many sig figs, radians per second. And if we divide that by 2 pi, that gives us 26,150 revolutions per second, which is a crazy number. I mentioned a minute ago to you guys who were logged in that a car engine turns at, when it's idling, somewhere around 1,000 revolutions per minute. And when you're driving down the highway, you're at maybe 5,000, 6,000, or if you're hitting the gas hard or in a low gear, you might get higher than that, even 7,000 RPM. It starts to redline at that point. It's not really good for the engine. This thing is turning 26,000 revolutions, not per minute, but per second. That is just nuts how fast this thing is spinning. And if it's got a magnetic field, it can be sending magnetic or electromagnetic radiation out as kind of a lighthouse beam, and we can detect those and measure their rotational rates. So this is not only calculated, but it's measured as well. And that's why I said when you take astronomy, you'll get these astronomical numbers. Anyway, that's it for this problem. I'm going to knit these two videos, two segments together, and upload it to Google Classroom or wherever I can put it so that you can see how to do this problem. And I will talk to you later. Bye-bye.